Kia ora. This is Reen Visser here at the School of Forestry, University of Canterbury. And while you're waiting for your next FGR conference speaker, I've been given the opportunity to spend a few minutes just promoting our professional development courses that are coming up in the 2nd to the 4th of November in Rotorua. So normally we would have held them here on campus, at least we have for the last 4 years, but in this case, assuming you're up in the North Island, we're coming to you, so up in Rotorua. There's 3 one-day courses that will run consecutively, so Monday, Tuesday, Wednesday. And just to share a little bit more detail about those courses. So the first course that we have is on how to determine a fair logging rate, or basically setting your logging rates. It's invariably a very difficult, potentially contentious process, but obviously it's critical for the financial success of both the forestry company as well as the contractors. So some of those key elements that we'll be covering is calculating machine system costs, as well as estimating productivity for a given system at a given site. We'll also be exposing you to the benchmarking, the FGR benchmarking database, and how you can best use that database to capture both cost and productivity information. And then also we'll focus on how to negotiate, how to best negotiate a logging rate and what some of those different negotiating practices are. Very fortunate to have Keith Raymond join me as instructor for this particular course. On the Tuesday, looking at designing stream crossings, obviously critical to protect our waterways under the Resource Management Act. Be providing an update on forest road construction practices, look at some of those main stream crossing design considerations, teaching you how to calculate flood flows using different methods, and using those methods to also design your culvert as well as get the size of your culverts right. That's assuming you're building a culvert type crossing, but we'll also really be focusing on your bridge options, and intends to, in that it's often best to go over a waterway than it is to stick a culvert in a waterway. So we'll be looking at the advantages of some of those modern bridge options that we have. Finish off by looking at some of those new capabilities in RoadEng, latest software that's out there, and it includes being able to design landings in there, designing spur roads, as well as there's a new module available in RoadEng 9, which is cable logging planning. So you can actually do your cable yarding analysis within RoadEng now. Campbell Harvey is going to help instruct that, as well as Dean Nielsen from Hancock, a true expert on designing stream crossings. The last workshop is all about managing harvesting residues. We know that these accumulations are both a risk, but they also present a real value opportunity for our industry. So we'll be stepping through some of the definitions, understanding the issues, studying the existing guidelines, as well as looking at some of the effects that your choice of harvesting system and harvesting practice can have on the generation of harvesting residues. Finish out by looking at biomass marketing opportunities and showcase some of the successful case studies that we've done. Again, it's myself, Campbell Harvey, and Keith Raymond will be bringing in some of the FGR research work, like the helicopter grapple, as well as the fixed head felling study that they have been directly involved with. So if you're interested, how do you sign up? There is a cost involved. It's $300 per person per day to cover our costs, or it's $820 if you want to come to all 3. You just need to email me. I'll put your name on a list. And then if you turn up, we'll send you an invoice. But also please be aware that if Rotorua does go back up to COVID level 2 or higher, we will be postponing the event. So we're only going to invoice afterwards to avoid any sort of complications. So if you're interested, please do email me. We certainly look forward to seeing you there. Nice to get together and share some good information. Thank you for your time. Bye.
Welcome to day 3 of the annual Forest Growers Research Conference, coming this year, of course, as a virtual conference. I'm Peter Oliver, Forest Assets Manager for City Forests, based in Dunedin. Today, session 1 today is entitled New and Future Directions. Now, there are significant challenges coming down the pipeline for forestry, including climate change, new pests, constantly evolving and competitive marketplaces, and of course increasing pressure on our social license to operate. But there are also opportunities as our science, understanding and technologies reach new levels of sophistication and create new and perhaps previously unthought of possibilities. There is indeed no standing still, and forestry, as much as other sectors, needs to stay innovative and open to new science and new ways of thinking about and doing our businesses, to stretch the boundaries of what's possible, if you like. The session today then contains presentations on a mixed but exciting basket of forest research initiatives that, while diverse in their breadth, are uniformly innovative in their approaches and important for the industry's current and future progression across a range of fronts. First up, we have Graham Coker from Scion, who's a leading specialist in plant-soil interactions. A number of forest growers have already been engaging with Graham on his work on next-generation forest nutrition practices. And Graham has been researching the role that micronutrients play in many of the biological processes which drive crop growth. Today, Graham will discuss his findings on their role and what an increased focus on understanding and potentially manipulating micronutrients might mean for forest growers looking to enhance and optimize the growth and quality of their forests in the future. Following Graham, Grant Pearce, a senior scientist at Scion, will look at some of the past and current work being done to automate the important processes of both quantifying and phenotyping nursery crops. As a forest manager and end user of nursery crops, I am both aware of the difficulty, complexity, and uncertainty of these tasks for nursery growers, and yet of their importance for both a profitable and successful nursery, and of course for those of us who rely annually on nursery outputs. A related presentation will follow Grant's from Scion's Dr. Dave Pont, who has a background in forest mensuration. And many forest growers in recent times will have already encountered the work of Dave and his team, who are also exploring the use of remote sensing technologies, particularly UAVs, LiDAR, and imagery techniques to assist forest growers to measure, evaluate, and characterize a range of forest and site characteristics that are important for understanding and managing both forest quantity, quality, and productivity characteristics. This work promises to give forest managers ready access to vast and detailed quantities of forest data never before possible to access in a timely or affordable manner. And then changing tack a little, science scientist and modelling specialist Yu Lin, together with Dave, will present on work being undertaken to develop next generation growth and yield simulators. In some respects, this is a how to use all that data presentation. This is likely to be of particular interest to foresters from a resources background like myself, who are still reliant on a suite of growth and yield modelling tools, which are in some respects now well dated. The project builds on and utilises the forest phenotyping work. Justin Morgenroth is the Associate Professor, Postgraduate Director of Studies from the University of Canterbury School of Forestry, and he's up after this. Like most of the presentations, Justin's represents a summary of the work of a number of collaborating scientists. Focusing on durable eucalypts, Justin will present research that explores and models the complex relationships between a variety of eucalypt species, their success, and a range of site variables. The final presentation of the session comes from Thales West, I hope I've pronounced your name correctly, from the Land Use Economics and Climate team at Scion, whose focus is on developing a portfolio framework for managing risk and uncertainty, with a particular focus on two of the largest and looming areas of risk, namely future log price volatility and future changes in forest productivity due to climate change. All in all, this promises to be a very interesting and exciting set of presentations. And as in previous sessions, please submit your questions as we go through the presentations. And then the presenters will join us for about 15 minutes of live Q&A, following the final presentation. And now over to Graham Coker. Thank you.
Good morning, everyone. My name's Graham Coker. I've worked at Scion since about 2000 on behalf of forest growers in the nutrition area. Today I'd like to present on micronutrients. Micronutrients, how they might improve forest growth. Micronutrients found in very small quantities, compared with soil nitrogen, which is about 2,300 parts per million. Micronutrients are found at less than 100 parts per million generally. Examples are copper, zinc, boron, molybdenum, cobalt, manganese. Micronutrients in use today, forest growers treat 150,000 hectares of radiata a year with copper, copper being a micronutrient. You can see on the image on the right-hand side, back in 2008, so the distribution and abundance of dothrostromal treated areas. Boron is another micronutrient we apply to mitigate deficiency. More often we believe it's related to managing crop stress. So the question is, what other micronutrients should we be using? So more on the copper story. There's some evidence for widespread copper limitations. Here we looked at a genetics by environment trial series across diverse environments in New Zealand. And we generally showed that most sites were probably deficient in foliage copper levels. A couple of sites there were obviously treated with copper spray, and so they are a good indicator of some of the issues that might be underlying forest crops. Micronutrients have a very small range in deficient areas compared to adequate and toxic zone, compared to macronutrients. You can see on the right-hand table there that the parts per million for copper ranges in the deficient area about 2 parts per million. We've shown adequate as 4, or optimal was about 5.4. And so just applying treatments of micronutrients is a little bit more difficult because you've got to get the treatments right. So one of the really interesting things or challenging things about micronutrients also that they are involved in the biological processes. Here we've got an image of the periodic table. You can see that a lot of these micronutrients are associated with cofactors or enzymes or genases that are complex compounds driving growth, at the process level. And so that's quite unique. In terms of a history of forest nutrition, it sort of developed after identification of second rotation deficiencies. They looked at the macronutrients of N and P, copper, potassium, magnesium ratio became a concern. So as we get closer to 2025, we're tending to head towards these micronutrients and other enzymes that we might be able to manipulate on forest growers' behalf. Here's an example of nitrogen fixation process that is influenced, as one of these important biological processes. And it's important to forest growers because symbiotic nitrogen fixation is one of the most promising and immediate alternatives. Over in Europe, they're already restricting how much nitrogen could be applied. And so we're looking for alternative ways to enhance the natural site nitrogen levels. Wood quality, it's another way that we can influence lignification processes using micronutrients. There's a complex compound called superoxide dismutase, which is a catalyst. Its function is to scavenge free radicals produced by plant stress. Generally, there are three types: the copper-zinc combination, there's a manganese, and there's an iron combination. So if we applied a treatment using these micronutrients, copper, zinc, manganese, or iron, we might be able to mitigate crop stress and improve control over lignification processes in radiata. Also, there are some options around manganese, which seems to provide an essential catalyst function in photosynthesis to split water for plant energy. So an important hypothesis that we'll be following is manganese plus calcium as a treatment could improve water efficiency of forests. And that's going to become more important as we head into climate change influences. So a lot of these micronutrients are complex, and they're reasonably well studied in the international literature. Here we've got an example of boron, and as recently as 2008, there's quite a controversial view posed, and there's been a lot of discussion whether boron is an essential element or related to toxicity in the cell walls and reducing stress in other ways. And so, you know, we're still at the cutting edge of a lot of the science, and it's developing over time. So the key for us as forest growers is to improve micronutrient monitoring. You know, this is going to allow us to understand effects in the future, and so growers need to include more of these analyses of micronutrients. Micronutrients accelerate biological growth processes, and we've identified some promising treatment options in our review, and so we think this is worth exploring more on behalf of forest growers in the future. Thank you very much for your time.
Hi, my name is Grant Pierce. I'm a remote sensing scientist at Scion Research. Thanks for inviting me to talk at the 2020 virtual edition of the FGR conference. My presentation covers FGR-funded research on nursery automation and phenotyping. We wanted to develop methods that would allow us to rapidly assess and count nursery crops in a way that was suitable for both automation and phenotyping. And at the same time, we wanted to test new sensors that had become available, which could allow us to count seedlings and measure their height at the same time. This project expanded core-funded research that we did in 2017. In the previous research, we showed that cross-correlation template matching, a very simple image processing technique, could achieve 90% accuracy where the image quality was high enough. However, this method achieved low uptake because it required dedicated software and it was very slow to make predictions. During this same work, we also noted that when you generated orthomosaics from your overlapping UAV imagery, you could actually get a reasonable estimation of seedling height within the beds. So based on this work, we know that getting counts of our seedlings from UAV imagery is straightforward. And we also knew that we could get some idea of seedling height as well. But there is one fundamental issue that we identified when we were doing this work. And that's that all of these results are based on a process called orthorectification. And there are significant drawbacks when trying to use orthorectified imagery for phenotyping or automation. Orthoimagery offers us consistent scale and perspective, but it also requires that we fly our UAV up and down the seedling beds with up to 80 to 90% overlap. In addition, we also have to take this imagery and run it through dedicated processing software that can take hours or days to produce the full orthomosaic. In addition to taking a lot of time to capture, orthorectified imagery also loses an enormous amount of detail and spectral purity. If you contrast the quality of the imagery obtained here on the left-hand side, this is orthorectified imagery captured from Scion's UAV, with the detail that we get off the raw imagery straight off the UAV here on the right-hand side, we can see that we lose detail that would allow us to detect this weed outlined in red. In addition, we can't use orthorectified imagery to extract these reflectance spectra here in panel C, which would allow us to detect nutrient differences at the level of the individual seedlings. To test our objectives, we established a trial in Scion's nursery containing 3 beds of radiata seedlings. Within each bed, we selected a minimum of 30 rows of seedlings, and each row of seedlings was measured at monthly intervals alongside the ground truth data captures. We tested 3 camera-based systems for measuring seedling height. The first was the Intel RealSense, a camera based on stereo depth estimation. The second was the Stereolab Z, a stereo camera based on visual inertial SLAM, and the last was the Microsoft Azure Connect, a camera based on time of flight ranging, which is a class of sensors that's increasingly available in consumer-grade smartphones. After a successful trial setup in November, we carried out a calibration run in December 2019. We initially scheduled monthly field and UAV height measurements. However, due to the level 3 and level 4 coronavirus restrictions, we lost 3 of the measurement dates. Because of this, we deemed that it was impossible to develop an accurate height growth curve for the seedlings, and we could not conclusively test the sensors. We had to abandon the height estimation project and refocus on other aspects. So we knew from our previous research that counting seedlings off orthomosaics is relatively straightforward, but we also knew that we could improve in certain areas. So we wanted to develop methods that would make it easy to deploy, that would be scalable and generalizable to large seedling beds, and that could handle complex scenes, potentially containing weeds. We also wanted to get methods that could go beyond counting to allow us to actually delineate individual seedlings, which is a key requirement for phenotyping. Before we can count the seedlings, we have to tackle a much more fundamental task, which is how do we acquire imagery over these very long seedling beds that can contain tens of thousands of seedlings. The first method we trialed uses direct georeferencing. In this approach, we take our UAV and camera and we equip it with a high-precision GPS. Then what this allows us to do is fly the seedling bed in a single pass with overlap requirements reduced from 80 to 90% down to 40%. In addition, the imagery that this process produces is georeferenced to within a few centimeters of its true location. Direct georeferencing greatly reduces the impact from the orthorectification process on the final image quality. It means that we don't have to do any aerial triangulation, but we do have to have a high-precision GPS, and in addition, we also have to have a carefully calibrated camera. Requiring a high-precision GPS and a calibrated camera does impose some limitations on widespread adoption. So what we did was we trialed a second method based purely on computer vision principles. Here what we do is we fly the bed once with 40% overlap at an altitude of 2.5 to 3.5 meters, and then we apply some corrections to get undistorted images. We take this undistorted imagery and we use a combination of algorithms called sift and ransack to build a continuous panorama of the seedling beds. You've used similar algorithms if you've ever generated a panorama using your smartphone. These algorithms look for common features in overlapping imagery, and they use these to essentially tie the images together into a continuous panorama. Once we had methods to capture imagery of these long seedling beds, we needed to develop algorithms that could count the seedlings they contained. Our first approach focused only on speed and accuracy, and we chose a neural network architecture called the darknet. This is a very fast framework that allows us to rapidly count seedlings off of the panorama. The second approach was slightly more sophisticated. Here we wanted to move beyond detection to do instance segmentation, where we actually draw an outline around a circular area containing the bulk of the needles for phenotyping applications. To do this, we had to capture labor-intensive annotations by drawing polygons around the outlines of hundreds of seedlings. Then we fed these to Detectron 2, a neural network system released by Facebook AI's research. The last topic we addressed is something called microplot extraction. Here, what we do is we aim to capture the best of both worlds. We generate an orthomosaic from overlapping UAV imagery, and then what microplot extraction lets us do is it take the real-world corner coordinates for each of these blocks that might be allocated to randomized treatments, and then we use a series of software scripts, and we go from XYZ coordinates in the real world to 2D coordinates in the raw input imagery. And this lets us automatically extract raw, unrectified imagery for use in phenotyping. The results from the direct georeferencing approach to generating long imagery over the seedling beds were excellent. Overall, it produced very high quality orthomosaics, minimal artifacts, and it was georegistered to the centimeter level. Most importantly, it allowed us to do this with up to 50% less overlap in flight time than a traditional orthorectification approach. We also used the imagery from direct georeferencing to test microplot extraction. What you can see here is a orthomosaic generated from the direct georeferenced imagery, and here we've got a simulated trial block. What we can do is we can take the corner coordinates here, we can use microplot extraction to go from the orthomosaic to the raw unprocessed imagery, and then we can overlay the 3D coordinates of the trial block into 2D positional space here on top of the raw imagery and extract just the pixels that belong to this treatment block. What about our second approach, where we try to take a single pass UAV imagery with moderate overlap and we try to turn it into a panorama? Well, the first approach, where we used sift and ransack from OpenCV, worked fairly well. But what we found was that the no-code approach that we trialed using the commercial software PT-GUI produced extremely high-quality panoramas with virtually no loss of detail and very few seam lines. This is important because it's a no-code solution with a relatively low cost, and it produced excellent results in a short amount of time. A common issue with both of the methods that we trialed was the generation of automatic type points over seedling beds. What you can see in this figure here are the automatic type points generated, in this case from Pix4D, but the results were the same for all of the other methods that we trialed. You can see that most of the matches occur in the ground around the seedling beds. And this figure over here shows that where the software thinks it's found some matches, it's actually looking at very different objects. But those matches found around the ground are largely correct. We actually ended up leveraging this by laying down regular markers alongside the beds to facilitate improved image matching using all of the techniques that we trialed. We couldn't wait for the end of the trial to do all of the development work, so what we did was we arranged to do a mid-rotation capture. This was done in November, and here what we did was we actually asked the nursery staff to hold off applying herbicide so that we could let the weed level build up in between the seedling rows here. Then what we did was we annotated just 25 images and fed them to our instance segmentation model. We took these 25 annotated images and we used them to train our mask RCNN instance segmentation algorithm. We were very surprised to see that we got 86% detection accuracy on a test set of images that were completely withheld from model training. This turned out to be an important finding because it showed that these counting algorithms can also be trained to work with much younger crops. The imagery generated from the panorama and direct georeferencing approaches was far too large to be used with our deep learning models. So what we had to do was we had to use an approach where we take these long images and we tile them before we run them through our models. What we do is we take a subtile, we record its position in the overall panorama or long orthomosaic. Then we take that subtile and it's small enough that we can run it through our trained model. The predictions we get back can be recombined with the information on the tile's original position to transfer the location of these individual seedlings back to their source within the overall panorama. The darknet model that we trained just to rapidly detect seedlings produced excellent results. The precision of the model was 96% and the sensitivity was 92%. Importantly, we achieved this using a Tesla K80, which is the lowest cost cloud GPU for training these types of models. So although it took 6 hours of training time for the model, we were able to detect all of the seedlings in a bed in around 2 to 5 minutes. This is important because it means that not only is the darknet algorithm accurate, but it's scalable, potentially to tens of thousands of seedlings. This slide shows the results of the darknet algorithm applied to the full panorama using the tile predict aggregate method that we described earlier. What we can see is that there are some false negatives towards the edge of the beds, particularly in seedlings that were too short to be topped. This is because our training data was skewed towards topped seedlings, and it resulted in a slightly lower sensitivity. We end up with a few false positives as well, usually with seedlings that have more than one leader. However, overall, the results were excellent, and most of the errors could be corrected with additional training data. The results from the segmentation algorithm were equally impressive. This is the mask RCNN algorithm that looks to both detect seedlings but also to segment out the individual crowns. The test set accuracy in this example was 91%. We set our overlap threshold quite high because we want to do phenotyping, so only predictions that overlap ground truth by 50% are counted. But overall, we still see here very accurate segmentation of the crown area. Once again, small training data set, but most of the seedlings are identified with high confidence, and the key crown area that we're interested in for phenotyping was accurately segmented out by the mask RCNN algorithm. Aside from the loss of the height trial, the overall conclusions from the study were very positive. We demonstrated 2 new methods for imaging long seedling beds using direct georeferencing and panorama generation. Importantly, both could achieve success using a single flight of the UAV with just 40% image overlap. The PT GUI solution offered a low-cost, no-code solution to generating high-quality panoramas of the seedling beds. The darknet algorithm achieved 96% precision and was extremely scalable. In combination, both of these methods are likely to be able to image long seedling beds and count tens of thousands of seedlings. From a phenotyping perspective, the results were particularly encouraging. We validated microplot extraction in beds of radiata seedlings, and what this will let us do is set out large randomized trials in our open-grown nursery conditions, and it paves the way for automated analysis pipelines. The instance segmentation algorithms will further help this, and they can clearly delineate and detect seedlings at multiple ages. And I believe that the accuracy of both of these models would be further improved with additional training data. The key message I would like you to take away from today's presentation is that the tools and groundwork are ready for large-scale nursery phenotyping. We've met all the critical requirements for automation and phenotyping, and now what we need is a clear implementation pathway and a use case. And I hope to continue this line of research in partnership with Scion and the forest industry. Thank you for your attention today, and I look forward to taking your questions at the end of the session.
The time to stop runaway global warming is running out. Fast-growing forest trees are the most effective way at this time for us to fight climate change. They suck carbon from the atmosphere. That's a big environment plus, and there's more jobs and income if you grow trees than farming sheep and beef. That's why so many smart farmers are so bullish, planting out trees and loving our forests.
Morena, my name is David Pond. I'm a remote sensing scientist at Scion, and I'm going to present on recent developments in forest phenotyping. So, phenotyping for forestry. What is it? It's about characterizing tree growth in relation to genetics, environment, and management. We do this to understand the drivers of tree growth, and we do that by measuring and then fitting models and using those models to manage forest growth. And phenotyping is carried out at scales ranging from the whole estate through individual trees and even down to within tree. So I'll cover some recent projects we've done on area-based phenotyping in association with Hancock Forest Management, on tree-based phenotyping with Radiata Pine Breeding Company, and finally some work on tree stem phenotyping carried out using a Hovermap scanner developed by Emerson Australia. So in our area-based phenotyping project with Hancock's, the objective was to look at managing forest and estate productivity. The approach was to compile a wall-to-wall high-resolution grid of data at a 25-metre scale, and that data set is compiled by assembling information from three main sources. Firstly, phenotypic data itself, which quantifies productivity in the form of site index and 300 index in this study. Then we add information about genetics and management, and this information comes from the forest owner's stand record system. And finally, we add information about environment in the form of climate and soils layers. So when we put together all of these different data sources at such a high resolution, we create a very, very large data set. And a data set this big is just not feasible to tackle with conventional modeling methods. So we apply a methodology called machine learning. And we use machine learning to fit models to predict productivity right across the estate, taking into account the effects of genetics, environment, and management. And the images on the right there illustrate productivity in terms of site index at the top there, and then also illustrating one of the environmental layers that we input to the model. In both cases, we can see that there's complex variation in both the productivity and the underlying environmental layer in this case. Results from this project, we're able to fit models that would predict yield in terms of 300 index and site index right across the estate. The results here are for 300 index. The model had an R² of just over 0.9. The plot at the bottom indicates the predicted versus observed. And then the plot on the right shows us the top 20 ranked variables from the machine learning model. So the machine learning ranks the features, and we can see in the top 5, the features have been color-coded: yellow for genetics, green for environment, and blue for management. So in the top 5, we see that we have examples of all 3. And currently, this helps us understand what are the key drivers of the model and for this estate. And at the moment, we're working on using that model to help select the best genetics for different sites at that estate. In our tree-based phenotyping work, it's carried out in a genetics trial, but also applicable to forest stands. The approach is to detect individual trees and then generate crown metrics for those trees. So in this study, we did that using LiDAR imagery and RGB imagery. These are illustrated at the top and bottom on the right. And then in more recent developments, we've been working on also incorporating the ability to quantify environmental effects and competition effects on tree growth. So competition is illustrated in the middle image there. So we quantify the competition of a tree by taking into account its immediate neighbours and their relative size and proximity. Results have shown we can detect individual trees with a 98% accuracy and estimate tree height with an R² of approaching 0.9. We also have found that UAV LiDAR is probably the preferable image source compared to RGB, but both can be used. And the methods we've developed are helping us improve results from the analysis of breeding trials. But in work in the last year, we also found that the ability to quantify environmental and competition effects is a very useful input to the development of next generation tree growth models. And you'll hear a lot more about this in the next presentation by Yu Lin. And we also worked with Forest Protection Group here at Zion and found that our competition metrics were able to provide useful input in understanding the dynamics of disease. So we had data in this trial on Dothrostroma needle blight and red needle cast, and found that competition metrics helped explain levels of disease as well as growth rates and survival. So in the third area, we looked at characterizing tree stems. The objective here is really to automate the measurement of stem size, stem form, and branching. So in prior work, we'd found that when we scan from above, say with a UAV, we tend to have insufficient information on the stem to accurately characterize it. Meanwhile, if we scan from below, we can generate quite detailed information on the stem. And so the approach here was to use the Hovermap, which is a laser scanner recently developed in Australia. And it's illustrated here mounted to UAVs, but it can also be handheld, backpack mounted, vehicle mounted, so quite a versatile tool. And in this case, we were looking at data collected by scanning below canopy, illustrated at the bottom right there. In our results, we proved that the device is a very effective tool for forest laser scanning. Processing the data that we collected, we achieved a stem detection rate of 97%, and the ability to estimate DBH with an R² of 0.88, and very confident we can improve on that. And so currently we're continuing to work with this data, and us and our collaborators are working on automating these methods and linking them to virtual reality environments. Links are provided there for a video and web story that we compiled about our work with the Hovermap scanner. So conclusions, the area-based and machine learning approach is a very practical tool for forest managers to predict productivity across their estate, taking into account the effects of genetics, environment, and management. The tree-based approach to phenotyping is helping us get more accurate results from trials, and the recent developments around quantifying competition are proving critical to accurately describing tree growth. And then the work on below canopy scanning is showing that it's essential to take that perspective to accurately quantify stem size, stem form, and branching. And looking forward, we're working on developing a recommender from the area-based work to match seedlots to sites using the information from the estate that the machine learning methods have analysed. We're applying tree-level phenotyping to help develop better breeds faster. And then models of competition and tree growth are proving critical to unlocking the puzzle of genetics by environment, by management. And we're also interested to take further the initial results we had on understanding forest health dynamics. And so I'll just close by acknowledging that this research has been a collaborative effort involving a large number of people from within Zion and industry. Thank you.
Hello, everyone. My name is Yue Lin. I'm from Forest Systems in Sion. Today, I'm going to present some of our work on next generation growth and yield simulators. Thank you. The title is, today I'm going to present next generation growth and yield simulators. In New Zealand, currently, the models and simulators used for forest growth and yield have been normally classified as stand growth models. Those kind of stand models and simulators are not spatially explicit, means not individual tree have been identified in those models. And those model and simulators quite often cannot provide sufficient resolution of the yield predictions to solve many of the problems that facing forest managers. So there's a call for next generation forest growth simulators. We believe that the new simulators must represent the state of the art in forest growth simulators. And it also should address the requirements of forest growers and stakeholders. By doing this, we held 2 workshops and collecting the feedbacks and the needs from all our stakeholders and the forest growers. There are here is a list for the top 5 needs arised. First one, they ask not only just the growth functions. It means that in the model, the growth should of the trees should also include the mortality, size distribution, taper, and the tree competitions as well. This represents the mechanistic model rather than a statistic model. Also in the simulator, people require distance-dependent individual tree-based models. That means the trees must have their locations and should be spatially explicit. Also, in the simulator, people should have silviculture and management planning tools that they can use for their management. This simulator also need to be flexible framework that can add in extensions and functions such like carbon and wood properties for their future use. Also, the simulator should be able to handle dealing with big data, not only from PSP data that we currently have, but also from the modern technology collected data, such like the LiDAR data that can be also used for modeling purpose. So according to all their requirements, we comes to this idea, a new forest growth simulator, which called PyReady. Currently, this is still an alpha version, but we have developed a prototype showing the functionality of the simulator. As we can see, this simulator can meet the basic requirements from the stakeholders. It is not only the statistic growth function, but beyond that, we have a mechanistic growth functions. All trees, as we can see, have their exactly locations in the simulator have been presented. And you can use this also for your silviculture and management purpose. This model is very flexible that you can extend to other purpose and develop further model procedures and submodels and use on different platforms. This model is also be able to use multiple big data entry interface. So what's the special about this model? The most important thing is that our model is not a purely statistic model as old simulators used. It is based on mechanistic model, which we use metabolic scaling theory and dynamic energy budget theory. So all those physical and physiological processes have been considered in our model and represented. And our model also able to include the biomass allocation in the model, so you can consider different purpose use of the model for your real daily management. Our model also includes and represent the mortality of trees that can be due to local tree-tree interaction competition. And our model is also flexible, that you can also use your empirical growth functions for modeling purpose. So we really include not only the traditional statistic model, but also the mechanistic model. Also, our model is able to simulate the tree-tree interactions. By doing this, we develop this zone of influence approach. As you can see, each of the zone of influence of the tree represents the space, physical space, or the resource that tree can occupy. And the tree competition happens when their zone of influence overlapped. They compete for the limited resource that in the overlapped area, which represent different mechanism of resource competition that include the above ground competition for light and the below ground competition for the nutrient and water. And by doing this, we are also able to include different competition that happens among interspecific trees or intraspecific trees. Also, our model also represents the key processes that of tree environmental interactions, that environmental constraints on tree growth have also been included in our model, such like resource level and abiotic stress. That gives you the simulation of different tree growth when they grow in different environment conditions, which is also important when you consider site differences. And also in our model, we can also include spatial explicit tree locations. So each individual tree's location have been recorded and represented in the simulator. You can develop your own special deployment for your management purpose, such like to study different initial spatial pattern and the effects on tree growth and the size inequality. You also can use this to develop different management scenarios, such like different thinning strategies and also selective harvesting approaches. And by using this spatially exploit trees, you are also able to develop uneven-aged stands, such like mixed genotypes or species that can simulate more complicated structures of your stand, which cannot be done in formal models and simulators. Our model is also able to handling really big data, such like you can control the model settings and develop your own scenarios by using a user interface, but you can also import manually the sample plot data that used in a formal database such like PSP. And the special thing in our model is that our model can also import LiDAR data directly. So by using this approach, you can identify individual trees that have been detected and recorded in the forest. And you can also import this LiDAR tree cloud into the model and identify each individual tree and identify tree metrics that you use to derive measures of microsite and the competition, such like competition experienced by each of the tree. As you can see here in the figure, that middle one was identified by the LiDAR, arrow LiDAR, and the right model interface is imported data. From this, you can also start your simulation and make prediction on the future standard dynamics at individual tree level. Also, currently, our simulator already developed a graphic user interface, but we also make it, because it's based on really free platforms and very flexible. We also develop different interface that can be used from different platforms, such like this model is currently built on NetLogo, which is a JavaScript language, and people or end users can access the model from the web browser or their mobile devices easily. And we also develop R extension that can be used by the advanced users. They can use R to control the model, call the model, make their own settings, develop their own scenarios, and to run the model to collect the data for their further analysis. At the same time, our model is also able to communicate and connect to R that can call R functions for the analysis in the model at the same time. We are also developing a Python extension. Currently, it's under development. So for in the future, Python users can also use our model from Python and can communicate. Our model can also communicate with Python labs. So there's definitely more works that need to improve our model. So we already displayed and present this model to some of our stakeholders and end users and collect their feedbacks. We think that in the next 12 months, there are 3 key processes we would like to do for our model simulator improvement. First is the further development and improvement, especially the parameterization and the collaboration, so people can use the model for their real work and test the model. And also we are going to include more environmental factors, such like soil and topography. And also climate inputs will be also built into the simulator. So people can also use the model for making future predictions on their yield on the background of global warming scenario. And also we are going to improve the silviculture and management functions, such like fertilizing, pruning, and thinning, make all those management tools more easier use for managers. In the next 2 or 3 years, we are going to extend the model current function and the sub-models. We are going to include the wood properties, weed management, pests and disease, and also for fire functions into the model. And we are going to develop a connection between the simulator and existing model systems, such like YTGen and Forecaster, so people can also flexibly use this model and with the tools that they're familiar with. Also, we are going to develop more precise 3D visualization and more detailed tree architectures in our model. And the user interface and the visual recommender will also be developed for the easier use of the model. Thank you for your attention.
Our planted forests, a sustainable resource. Trees locking up millions of tons of climate change surplus carbon from the atmosphere, then storing it in our buildings. Standing forests, binding the landscape, cleaning waterways and absorbing floodwaters. A sheltering habitat for endangered birds. Forests, a thriving investment for generations to come. As places to ride your bike, go for a run, sweat or relaxation among the trees. Love our forests.
Good morning. I'm Justin Morgenroth, and I'm going to be presenting to you today on site species matching with durable eucalypts. So thanks for inviting me to speak to this group. It's an exciting opportunity to tell you about some of the research that we've been involved with here at the School of Forestry for the last few years. And though I'm presenting to you, this is really on behalf of a much larger research group, including myself, Professor Ewan Mason, Dean Meeson at Scion, Mark Bloomberg, an adjunct here at the University of Canterbury, as well as some postgraduate students, namely Siraja Selikan, who is now graduated with his PhD. He's actually working with Dean Meeson at Scion. We've got Daniel Bochniewicz, who's currently doing his PhD with myself and Ewan Mason, and Tyson Lee, who graduated with Masters a couple of years ago and has returned home. In any case, as I say, this is a really nice opportunity to be able to share our research with you. So thanks for joining us. So I'll start sharing my screen, and you can follow along with the presentation that way. Okay, there we go. So as I say, I'll be presenting to you my site species matching research with durable eucalypts on behalf of a much larger research group. So essentially, what we're doing here is trying to better match the species that we plant to sites within a given set of environmental constraints. And what we want to do is provide growers with alternative species that they can plant for different end uses and to match specific environmental constraints, I suppose. And a lot of the research that we're doing is to basically describe a set of key characteristics, things like growth and yield, survival, heartwood or sapwood formation, across a range of sites that have varying environmental characteristics. So this is essentially what it's all about. This is one of our sites. It represents a reasonably small site with Eucalyptus globoidea planted. It's age 6 Eucalyptus globoidea. And as you can see from the image, there's a range of I guess, survivals as well as growth rates. So of the ones that have survived, there are heights in there ranging from roughly 0.5 meter to 4.5 meters at age 6. You can also see a range of, I guess, topographic conditions, a range of aspects and slopes, as well as a small range of elevations. So those topographic conditions create different soil moisture availabilities, create different amounts of radiation interception. Just in general, they create different growing conditions for a species, and we wanted to understand how Eucalyptus globoidea and some of the other durable eucs responded to these siting effects. So PhD student Siraja Selikan, well, I should say PhD graduate Siraja Selikan, who's now working at Scion, undertook the vast majority of this research. And one of his outcomes was to basically look at height growth in response to some of these different environmental characteristics. So the first species that he looked at was Eucalyptus globoidea. And what he found with Eucalyptus globoidea was that at high levels of topographic exposure, where you might expect a high degree of wind, then the trees exhibited the least height growth. So trees grew shorter when they were exposed to high levels of wind. Another result that he came up with was that when Eucalyptus globoidea was planted in a concave topographic position, it also exhibited lower height growth. And then finally, he found that Eucalyptus globoidea planted on the mid-slope, so not at the top of a ridge, not necessarily at the bottom of a valley, but sort of in the middle there in the mid-slopes, those had the greatest height growth. So taken together, what this suggests is that Eucalyptus globoidea is certainly intolerant of wind. It doesn't like that exposure to winds. And also it's intolerant of high soil moisture or potentially frosts in gullies or depressions or low down in valleys as well. So Globoidea is not a species to grow in your valleys, not a species to grow in areas prone to frosts, because it simply doesn't exhibit, I guess, a great height growth response to those conditions. What about Eucalyptus basistoana? So basistoana exhibited some similarities to Globoidea in that it also did not like exposure to wind, but in contrast to Eucalyptus globoidea, basistoana preferred concave topographic positions. And it also preferred being grown on toe slopes. So what this suggests is that while it's intolerant of the windy conditions, it actually has a greater water requirement, or at least a greater tolerance to soil moisture relative to Eucalyptus globoidea. Sirajus also looked at the influence of siting on survival. And ultimately what he found with this study was that Eucalyptus basistoana showed greater rates of survival than did Eucalyptus globoidea. And he showed that Eucalyptus globoidea mortality increased in hollows or gullies or deep in valleys as well. And this again makes us think that it's possibly intolerant of wet feet, so wet conditions, or potentially frosts in those gullies or hollows as well. Together, Sirajus's research produced the ability to develop these growth and yield models. So he's been able to essentially measure the mean top height in the basal area for a variety of different plots for globoidea across the country. The measured data are the black lines, and then he's been able to model that as well. So the blue lines represent the modeled data. Now, what's been nice, I guess, is that Professor Ewan Mason's been able to take those results and turn them into a product that anybody can use. So I'm just going to click on this link here, and that's going to bring up a web page. I'll have to change my screen sharing so you can see that as well. So let me just change that. There we go. Okay, so now I'm hopeful that you're seeing a website that shows growth and yield for Eucalyptus globoidea. And what it allows us to do is enter some starting values, and then that will model the volume that you can expect from that particular species. So let's start with a starting age of 4, a mean top height of 5 meters, a basal area per hectare, also 5 meters, stocking of 1,000 stems per hectare, and a final age of 25 years. And then we'll introduce some thinning regimes as well. So let's create a thin at, let's see, 7 years down to, let's say 700 stems. And then again at 15 years down to 400 stems. So we'll register those thins. And then if we click on go, we end up with this, this growth and yield table that shows age and years in the first column, expected mean top height, basal area, and volume as well, down to age 25. So this is a nice little tool that anybody can play around with, and it's based on the modeled results of Sirajus's research for globoidea. So I will go back to sharing the PowerPoint presentation. Here we go. So what's the benefit to growers? Well, essentially the research was designed to better inform growers about the various factors that are influencing durable eucalyptus survival, growth, and yield. And I think we've got a better understanding for at least Eucalyptus globoidea and basistoana now as to where we should be siting them. And then the secondary objective, I guess, is that with the tool, the online tool that was developed by Ewan Mason, we can give growers more certainty around expected growth and yield. So on to the next little bit of research. That previous research was limited in a sense by the lack of PSPs around the country. and essentially the lack of environmental variability in the existing PSP network. So what master's student Tyson Lee did was he basically performed a desktop exercise, a GIS-based analysis, where he looked at where we could strategically expand the PSP, the permanent sample plot network, for Globoidea and Basistoana. And so what you see is a couple of different maps there, on the left for Globoidea, on the right for Basistoana. And what it shows is the current permanent sample plots, those little blue dots, and areas where we should try to establish new permanent sample plots for each of those species, based on the assumption that we want new permanent sample plots to have different environmental conditions than the existing plots. So you can see the dark green areas in either of those maps. Those are areas where we should try to strategically expand our PSP network to establish permanent sample plots in environmental conditions that are not currently represented by the existing permanent sample plot network. So this is really going to inform where we establish our new permanent sample plots, such that future studies will benefit from the full range of potential growing conditions. So up to maybe last year, we'd undertaken all of that research. Those results on preliminary survival, growth, and yield, those were important first results. But we wanted to better understand stem volume and taper. And heartwood description was also a key product because of its durability. So with that in mind, PhD student Daniel Bociniewicz came along, and he basically undertook a data collection program where he visited a variety of different sites around the country, and he destructively sampled 74 trees across a range of age and sizes. And you can see the types of forests he was working in, the samples that he collected there in the top right image, the logs that he'd felled in the bottom left, and bottom right, what you see is the heartwood stained in each of those discs. So here's a brief sort of description of those destructively sampled trees at those 7 sites. You can see diameter breast height along the x-axis, height along the y-axis, and you can see a good range of tree sizes that he has successfully acquired data from. And what he's been able to do with that data, he's been working quite extensively with Professor Mason to develop these compatible models that basically describe the volume of heartwood, the volume of sapwood, the total wood volume, the volume of bark for these sample trees. So these are just 3 specific examples. We see tree number 18, tree number 4, and tree number 45. And you can basically see the heartwood in that sort of dark red line, the total wood in that sort of orangish line, and then the bark in the pink colored line. So you can see these basically more detailed descriptions of the wood that you're going to get given different sizes of trees. So what we've then turned that into is basically a little Excel spreadsheet that you can type in a variety of starting values into. So you type in a height and diameter. So for example, over here on the left, you have a tree of 35 meters in height with a 45 centimeter diameter, and that predicts a total heartwood volume of 0.78 cubic meters, a total sapwood volume of 0.42 cubic meters, which together add up to 1.2 cubic meters. You've got a total bark volume of 3/4 of a cubic meter, and the total volume as a whole is 1.97 cubic meters. So you get a rough idea of the breakdown of different products that you can expect from a given felled log. So what are we trying to do here? How is that of benefit to growers? Well, basically it gives growers a greater understanding of how much total wood they're going to get, how much sapwood they're going to get, how much heartwood they can expect to get, given a particular height and DBH measurement. Things that we're currently working on and we'll be working on over the coming summer are to determine siting effects on heartwood formation. So there's some suggestion that depending on the site characteristics, the amount of heartwood formation may differ, and that's something we'd like to experiment with. So we'd like to try to understand that relationship a little bit better. So we're going to characterize some sites, we're going to collect some cores and undertake measurement of those cores for heartwood and sapwood. volume, and then we're going to model the effects of those site characteristics on heartwood formation. So that's my presentation. Hope you enjoyed it. Those are my details. Feel free to get in touch if you've got any follow-up questions. All the best. I'll stop sharing now and end the presentation.
Hi everyone, my name is Thales West. I work here for Scion. And today I would like to show you some of the results from a work we have been recently developing here, looking at forestry, climate change, and risk. And here we have it. So specifically, I would like to talk to you about a work that we call diversification of forestry portfolios for climate change and market risk mitigation in New Zealand. Okay, so we know that climate change will affect forestry in New Zealand. Here we just have two figures as examples of how precipitation and temperature will change. And we know that those changes will affect productivity, right? So there is a need to mitigate future risks imposed by climate change to forestry investments. How do we propose to do that? Well, with investment diversification, right? So any type of investment is arguably associated with an expected level of returns and an expected risk. Diversification reduces the exposure to risk, and a common path towards diversification is to reduce risk by investing in a variety of assets, okay? And that is called portfolio. Just as an example, that's exactly how the KiwiSaver works. All right, so how do we construct an optimal portfolio? Here we have an example of a stock, right? This is one stock that you can buy from the stock market. What you see here is a time series of the price of this particular stock, right? So from this type of information, this time series information, you can obtain information about risk or volatility, and you can also obtain information about returns over time. Okay, and an optimal portfolio is the portfolio that maximizes the expected return for a given amount of risk, or that minimizes risk for a given expected target return. Okay, and I'm highlighting minimizes because here in this work, we constructed two types of portfolios. One is called low target return, forestry portfolios. The other type is called high target return forestry portfolios, and all of them are based on a minimization problem once we set up a given level of return. Okay, but how our forestry portfolios look like? What are those forest portfolios that I'm talking about? Okay, well, first thing is that we're not looking at prices per se, but we're looking at annualized forestry returns. So we have a time series for that, okay? And these returns, they're just annualized net present values of the forest plantation that we're gonna simulate here. So we're talking about dollars per hectare per year, okay? We are also talking here about climate change, so we're talking about the future, right? So to be able to simulate these returns into the future, we obviously need to apply some simulation methods. And our simulations are basically based on two components. One is the future forest productivity under climate change scenarios. We're talking about log volumes per hectare, as well as future log prices. So price per log. Okay, we're gonna put all this information together in order to construct this annualized forest returns time series, and then we're gonna use them to construct the portfolios. Specifically, the steps that we took here were, first, we simulate future climate scenarios for 2020 to 2090, and the scenarios are based on 6 global climate models. And these models consider two types of climate change scenarios called RCPs, okay? And here I'm gonna show you the results for RCP 2.6 and 8.5. And basically what we have here is that with RCP 2.6, we have a slightly warmer planet with RCP 8.5, we have a much warmer planet. Okay, we're going to use the output from these 6 climate models to simulate future forest growth. We're talking about Pinus radiata regimes here, using the forest growth model called 3PG. Okay, we're also going to forecast log prices for 2020 to 2090, and those forecasts are based on projections from this model called Global Timber Model, along with historical log prices from New Zealand. And finally, we combine these pieces of information to compute the annualized forest returns. And then we use that information to construct our so-called forestry portfolios. Okay. So let me show you some of the results that we have. In terms of the future climate scenarios, specifically for our study site, which is located north of Christchurch, here is how our climate variables that we used in 3PG look like. Okay, again, we have the 2 different RCPs here. We have climate variables such as rain, sub-zero days, maximum and minimum temperature. Okay, and of course we have in each panel 6 different lines. They come from the 6 different climate models that we used. Okay, so we are using this information to simulate forest growth with 3PG. And here is an example of how 3PG simulates forest growth. Okay, here we have a forest that is planted in 2020, harvested in 2050. What is really important for us is the volume at harvest, because that is the volume that has value. We have 6 growth paths here, and they all come from the 6 different climate model data. All right. And we also simulate growth for 2 different Pinus radiata regimes. One is the T7S300, where we have thinning at age 7 and final stalking of 300. And the other regime is 79S600, where thinning happens at age 9 and our final stalking is 600. Okay. All right. So if we simulate these volumes at harvest here for each year and plot them from 2050 to 2090, this is how they look like. Okay. Again, we have the RCPs here, we have the 2 regimes, and we have 6 lines in each panel corresponding to the data from the 6 climate models. So what we did was we created averages based on these 6 different lines in each panel. And we constructed confidence intervals along these averages, okay? And we used this information to create a high, average, and low forest productivity scenarios, okay? So keep those in mind. We have 3 different forest productivity scenarios. We're gonna work with them. Our portfolios are gonna be based on them, okay? But we also need to know the log rate volumes associated with these volumes at harvest, right? Because those are the volumes that actually have value. How do we do that? Well, we go from volumes at harvest to log rate volumes, considering these 6 different grades here, by multiplying the wood volumes at harvest by the log grade percentage from this table here. And because we can play with these different percentage, we can actually go from 2 regimes to 4 regimes, having each of our original regimes under pruned and unpruned versions. Okay. But we still need to know the future log grade prices. How do we do that? Well, we adopt some projections from this so-called global timber model, along with some volatility that we extract from historical log price data for New Zealand. And we combine all this information into some Monte Carlo simulations. And then this is what we have for the 2 RCPs. Okay, so here we have the historical data, and here we have the projections after 2020. And again, because we have different ranges here, we can use them to create high, average, and low log prices scenarios. In this example, we have those scenarios for P1. Okay, all right. Now, all we need to do is to combine the log price scenarios and the log volume scenarios to create the annualized forestry returns that we're going to use in our portfolio analysis. Okay, so how do we do that? We basically multiply the log rate volumes by their prices, sum them up, and annualize them. And then we have the annualized forestry returns here. Okay, so again, we have the two different RCPs, we have our 4 different regimes, and in each panel, we have a line or a time series that corresponds to any specific scenario. Okay, we are going to construct one forestry portfolio per scenario and per RCP. And looking at the scenarios here, you can see that we have low, average, and high log prices combined with low, average, and high productivity scenarios, okay? Looking at this at once, it might be a bit overwhelming, right? So let's just focus, for the sake of an example, on one specific scenario, okay? Under one specific RCP. For example, high log price scenario, high productivity scenario under ICP 8.5. So here, what we have highlighted in green is 4 time series for the 4 different regimes. And we're gonna look at this time series here, and we're gonna extract some information from them associated with returns and risks. And based on those returns and risks, we're gonna construct our portfolios, okay? And here is our results, our portfolio results, here for the low target return portfolio, okay? Each bar here that you can see is an independent portfolio, but let me just walk you through this graph. What we have here is the log rate scenarios, low, median, and high, versus the forced productivity scenarios, high, median, and low, for the 2 different RCPs. So depending where you are across these scenarios, this range of scenarios, you have an optimal portfolio based on our low target return objective, okay? If we change the objective of our portfolio, if we go from the low target return to a high target return, then our portfolio also changes, okay? And in this case, we started to see the presence of the T7S300 prune regime, which is, according to the data that we used, associated with the highest returns, but also with the highest risks, okay? So here we have just 2 examples of our portfolios, okay? And with that, let me move into the conclusions and future research directions. Well, our results suggest that regime diversification can reduce climate change and market risks, okay? But this presentation is really about the framework that we are proposing here, how to create these forestry portfolios, not the results per se, okay? We can apply this framework based on input from forest managers, different input, different assumptions, okay? For example, we can consider different regimes. We could also examine different tree species as part of portfolio options. Right now, we're only focused on Pinus radiata. We can also consider other sources of risks, for example, future diseases or forest fires. And we can expand our analysis to other sites or other regions. Okay, and that's all I have for you. Thank you very much.